Log on, tune in, find out. Another good idea from Cambridge.
Come to the second afternoon session. And talk will be given by Chunxiong Zheng.
Hello. Wait.
Was not too bad what I said.
Yeah.
And he will speak about global ray tracing ignoring caustics. Please.
Thanks, Chair. And first of all, I would like to thank Professor Peter Markovich and Professor Xu Jin for giving me such a chance to report in this famous university. And I feel honored, greatly honored. Today I will talk about very old, but it seems also very hot in the last several years topic. This is the high frequency wave simulation of high frequency waves. The title is Global Ray Tracing, Ignoring Caustics. So I would like to first of all, I will go back to the classical geometric optics method. This method is based on the so-called the WKB ansatz asymptotic series solution for the linear wave-like equations. The WKB ansatz is like this. I think everybody knows. And here S is a real phase function, and A epsilon is the amplitude function, and you can expand it into an asymptotic series form like this. And for the moment, I would like to consider the scalar linear wave-like equation. So it's quite a general form. And if you substitute this asymptotic series solution into this equation and equating different powers with respect to epsilon and to the leading order, you derive a phase equation for the phase function S. It's like this. And then for the higher order terms with respect to epsilon, you get a sequence of transport equations for AJ. And in principle, if you solve this phase equation to derive the phase function, the real phase function S, after that you can solve this sequence of transport equations one by one. Okay, first you solve, you get A0 and then you get A1, and this equation, the phase equation, is the first order PDE, and you can solve it with the retracing method. This is the method of the characteristics, and you can also solve these transport equations along the specific trajectory, and you got all those terms. It seems nice, right? Because you change the resolution of this PD equation into a sequence of OD problems. That's the great benefit for this method, right? At least from the computational point of view, it's a great reduction of complexity. But things are not that easy. That's the caustics. If you, here is an example. If I consider the homogeneous Helmholtz equation, and here the velocity field is variable like this. It seems a Gaussian bubble here, a Gaussian bubble here, and suppose the plane wave travels to the right direction, and due to this inhomogeneity of this velocity field, the rays will diffract it after it penetrate this bubble. And in this two region, you got multi-phased region, and this is the single-phased region, and this is a two-phased region. And on the interface, if you solve the equation in this way using the retracing method and the amplitude function later, the amplitude function will blow up here. This is so-called caustics. And in this region, close to the caustic, and the retracing method does not work. This is the basic argument, and it lasts for many years. Okay. So, how to solve this problem? There are many remedies and or different solutions to solve this problem. First, I would like to say make a brief review on the canonical operator theory by Maslow. Maybe many other guys, but I learned this from Maslow's book, so I just mentioned his name. And the basic idea of Maslow's canonical operator theory is like this. Okay, suppose at the initial time the phase function is single valued, and due to the Hamiltonian flow, this Lagrange curve in one-dimensional case will deform. Okay, will deform, and later on, this function, this curve, will be multi-valued if you insist on projecting this curve onto the coordinate, the real space. And you can see in this region, this phase function, this phase curve becomes multi-valued. And here, these 2 points are just the two caustic points, right? The Maslow's idea, the canonical operator theory, is doing this because he realized that why caustic happens, why there are caustics, because you are insisted projecting the phase curve, the Lagrangian curve, the Lagrangian manifold onto the coordinates, the real space, because you insist on in using the coordinate representation of the wave function. I believe that this is the motivation. This is the motivation of Maslow to develop this canonical operator theory, because he realized that if you decompose this Lagrangian manifold into different parts, and you use different representation on the different parts. Okay. For example, on this part, you project it onto the real space, but this part, if you project it into the real space, it becomes multi-valued. But if you project it into the momentum space, it's single valued, right? And for this part, okay, you can project it into the real space. It's still single valued. And Maslow's basic idea is, okay, on the different parts, he developed the formal asymptotic solutions, and finally, he tries to patch this formal asymptotic solution together by introducing the so-called Maslov index. That's his basic idea. He realized that the caustic problem happens because you insist in using the coordinate representation, right? This is his basic idea, I think. Okay, and but Maslov's method is very beautiful. His theory is very beautiful. You can read his book, read his book. But the problem is, if you use his theory to develop the numerical methods, you have to understand the structure of a Lagrangian manifold, right? And at least from the computational point of view, it's not an easy task, especially in high dimensions, right? So later, there are many different methods to in fact, this rightly explains why his theory is seldomly, rarely. In fact, I didn't see any work, at least from the numerical point of view, to implement his theory. I think that's the reason. And later, there are many different methods. For example, the big ray tracing method, I think by Banamo, and he used part of Maslov's idea to develop this so-called big ray tracing method. And later on, there are many mathematicians to develop the momentum closure method. And this method is based on the limiting Liouville equation, because if you do the Wigler transformation on the wave function, you get a Wigler equation. Wigler equation, and if you take a limit, and you got a Liouville equation, and this is justified by many mathematicians. Here I just mentioned a few, and Now, along this respect, the many works, and as I know, the earliest is by Enquist and Romberg in 1996, and later on, the many authors to follow in this direction, and this is so-called moment collusion method. But this method suffers from at least two difficulties. First, you have to have some a priori information on how much branches, if you project this Lagrangian manifold onto the real space, right? You have to have some a priori information. This is the same as the Maslows canonical operator theory, because this information typically is not easy to obtain. Okay, and then later, Professor G and Osher they initiated the level set method to solve this kind of problem. They are concerned with the observables first. They are concerned with the observables away from the caustics. Okay, later on they realized that, okay, this level set method can be also used to recover the wave field, but only away from the caustics. So around the caustics is still a big problem. Okay, and in recent years, many mathematicians they pay much attention to the so-called Gaussian beam method. Gaussian beam method, the benefit, as I understand, the most remarkable benefit is this method can resolve the wave field even around the caustics, but the accuracy is degenerated, in fact. Okay, and here I only mention a few, and I should remark that in the last 2 years, and this method has also been used to handle the boundary value problems of high frequency wave problems. These two papers, and of course you can combine these ideas together. For example, in 2008, Professor Jin and Dr. Yang they used the level set method combined with Maslows' canonical operator theory. They use the Maslow index. They can resolve the wave field away from the caustics and more accurately. Okay, this is the existing method, the existing remedies and the solutions. So what do we do? What I will report in this talk. In fact, I realized if we venture one step further, okay, only one step further on Maslow's footprints, then everything is done. It's very simple. Okay, Maslow realized you can project this Lagrangian manifold either to the real space or the momentum space or the mixed, so-called the mixed coordinate momentum space. But in fact, there are a lot of representation you can choose, right? The coordinate representation and the momentum representation are still too special. Okay, in fact, we can develop the so-called the fractional representation, and Maslow's the coordinate representation and momentum representation are just the two special instances. So in this talk, I will talk about this. To formulate the basic idea, I just take the one-dimensional Schrödinger equation as an example. Okay, how to do that? First, I have to introduce what's the fractional representation of wave function. The fractional representation is based on the so-called the fractional Fourier transform. Everybody knows Fourier transform. And what's the fractional Fourier transform? Fractional Fourier transform, you can think it as some kind of interpolation of the identity operator and the Fourier transform operator. It's defined like this, and here alpha is a real parameter. Okay, it's a real parameter. It in fact has a geometric interpolation. It's related on an angle, how you rotate the phase space. Okay, it's a real number, and the fractional Fourier transform is formally is defined like this. But you may say, okay, when alpha, for example, equal to 0 is singular, right? In this case, you have to understand this formula in the limiting case, and there's no problem. And here I listed some basic properties of this fractional Fourier transform. First, I call it the consistency. When the angle is 0, that means you do not rotate the phase space, okay? You do not do anything, then this operator, this fractional Fourier transform operator is just the identity operator. And if the angle is pi over 2, you rotate the phase space in the anti-clockwise direction by 90 degrees. Okay, it's just the Fourier transform. But here I use the Epsilon scale. This is almost the same. And the second remarkable property of this transform is so-called the group property. Okay, if you rotate first the phase space with the angle of beta followed by another angle alpha, then the effect is just you rotate the phase space with the alpha plus beta. It's easy, right? And you can understand it. And another property I will use frequently later is the invariant. That means the Gaussian coherent state function is an invariant function of this series of Fourier transform operator. Okay. And here there's some other transformation properties. And sorry.
Alpha equals 0, you have to say alpha.
Yeah, you have to understand in the limiting case. Limiting case, you take limit. Okay. And here is some other properties, but the most remarkable is this one. If you take alpha as a parameter, you can differentiate with respect to this parameter, and you get a nice formula like this. And it will use later to deduce the Schrödinger equation in the fractional representation. Okay. And I would also like to introduce the so-called translation operator. Okay. You give for any phase point in the phase space. And the translation operator is defined like this. You just shift the origin to the point Q and to the point Z. Okay, this Z is in the phase space. For example, here is the origin, and here is Z. For example, here is Z. You just shift the origin to this point. It's another representation. You change the representation, and here's the basic property of this translation operator. If you first you shift the origin to Z2 and then followed a shift to Z1, the effect is just to add up them together, but you get an additional phase term. Okay, you get additional phase term, and I introduced this translation operator like this because in this way it almost commutes with the rotation operator. Here, you remember alpha is the rotation angle. It defined as a rotation of a phase space, and here followed a shift. The effect is just that you first shift the origin of the phase space to this point, and then you do rotation. It's easy. You can just verify it directly. Okay. So what's the fractional representation? I just say, okay, here. If you use this, the normal representation is just a coordinate representation. Okay, if you do Fourier transform for the wave function, you got the momentum representation. But what's the fractional representation? Fractional representation is just, okay, first, given a phase point, for any phase point in the phase space, and a direction angle alpha. Okay, first you shift to this point Z, and then you rotate because the origin has already been shifted to here, and then you rotate it, okay, like this. So this is the new representation of wave function. You will realize that there are a lot of representation if you do it this way, okay? In particular, if you take the parameter as like this, the phase point Z is just the origin, and the angle is 0, it's just the coordinate representation, okay? It's the representation we like. And if you take the origin as the same as the original one, and you rotate it, with a 90-degree, okay, it's just a momentum representation. So here, these two representations is just two special instances of this fractional representation. Now we have a lot of other choices, right? So I would have to define the so-called moving frame. What's moving frame? Just now I introduced the fractional representation, right? You determine a phase point, and you given a direction angle, you got a fractional representation. Now, if given a Hamiltonian, and you change this frame according to the Hamiltonian flow, then I call it as a moving frame. Okay, the point changes follow the Hamiltonian flow, and the direction angle also changes. Okay, also changes. So this is so-called the moving frame. And so given a Hamiltonian H, you determine a Hamiltonian flow, and if I denote GT be the phase flow induced by the Hamiltonian H, then we could denote this moving frame like this. Okay, it's a displaced representation. It's a displaced representation. It depends on the variable t. Okay, this is so-called the moving frame. I would also like to introduce some terminology. The first one is so-called the sample phase curve. So what's a sample phase curve? Sample, a connected phase curve, because here I am only concerned with the one-dimensional case. So if you're given a connected phase curve lambda, I say it's sample if gamma admits a diffeomorphic projection on the tangent direction, tangent 9, for any z belongs to this Lagrangian curve. So the meaning is like this, okay, for any point. And here, because this is a Lagrangian manifold, you have the tangent plane. In one-dimensional case, it's a tangent 9, okay? Then you project this curve onto this line. If this function, if this curve is single-valued, if you project it into this line, then I say it's a sample. But for any point here, for any point, this one is not sample. This one is sample, but this one is not sample. This one is not sample. For example, if we put the phase point here, and then in this direction, you project this Lagrangian curve onto this line, it's not single-valued. Obviously here it's multi-valued. So this one is not sample. But you can prove, it's quite easy. For given any WKB function, okay? Any WKB function, I say it's a sample if the Lagrangian curve, if it's a Lagrangian manifold, is sample. This is another terminology. And given the Hamiltonian flow, I say WKB function is a sample up to time t. T is a fixed time point t. If the displaced Lagrangian manifold is sample for any t belongs to this interval. Okay. Later you will realize what's the importance of this definition. What's the sample? Okay. So here is a schematic map, and for example, at the initial time, the Lagrangian manifold is like this: is M, right? And the GT is the Hamiltonian flow. It will change. Okay, this curve will change. In the phase space, for example, at the time theta, it's like this, and at time t, it's like this. Obviously, M is sample. You can see here. If you put any point in the tangent direction, it's single-valued. Okay, but M is not sample up to time t. Okay, because here, if you put the phase point here, then you project this displaced Lagrangian manifold on this line. It's multi-valued, so it's not sample up to time t. But you can use the basic technique, the so-called partition of unity, to achieve this property. So given a WKB function, here I always assume the amplitude function A and the phase function S are sufficiently smooth, okay? And the empty function has a compact support. And I always suppose the Hamiltonian flow is sufficiently smooth. And you can prove it's quite easy. For arbitrary but finite time t, then there's a positive number sigma, and for any smooth function, you can take it as a windowed function. For any smooth function phi, if you multiply this wave function f with phi, it's still a WKB wave function. Okay? If the support of this windowed function is sufficiently small, then you can make this WKB function sample up to time t for any fixed time t. Of course, this sigma should depend on the time t, but if you give it, no matter how large t, there should exist such a positive number sigma. Okay, so you can just do the partition of unity and to separate this wave function into different components, and each one is a WKB function, and each one is a sample up to time t for arbitrary but finite time t. Okay, you can do it by the partition of unity technique. And here's a theorem. It's very important. So, hello. So given a simple WKB wave function, okay, like this, and I denote lambda as its associated Lagrangian curve. Then for any phase point on this Lagrangian curve, then you can express this wave function in this fractional representation. It's a fractional representation I just introduced, and it's still of the WKB type. It's still like this, and here this alpha is the direction angle. It's direction angle of this Lagrangian curve. Okay, and you can also determine this this amplitude function B by the amplitude function A and the phase function S tilde like this. And the most remarkable properties like is here at c equal to 0. This fixed function, the derivative and the second derivative is 0, because here you do Taylor expansion, you can find the next term is c cubic. Okay, this is an important theorem. The importance of this sample property is you can prove it just by the stationary phase method, the stationary phase theorem, and the sample condition is used to guarantee a unique long degenerate stationary phase point. Okay. Okay. Now I'll go to the Schrödinger equation. Oh my God. The Schrödinger equation. I want to express the Schrödinger equation in the moving frame. Okay. Here's the 1D Schrödinger equation. Here, potential V. You can make it depending on time t. It doesn't matter. So the Hamiltonian associated with this equation is just like this, and the moving frame in this case is like this, and these two equations are just the Hamiltonian system, and this one determines the direction angle, how it changes according to the Hamiltonian flow. And now I want to express the wave function in this moving frame. I denote it as this guy, and if you substitute this into this equation and do some calculus, you derive a Schrödinger equation, but it's expressed in the moving frame. It's a Schroeder differential equation. It's much more complicated than the original one, right? But later you will realize the benefit of this equation. Here I introduce some auxiliary functions. The V tilde is just the residual of the local quadratic approximation of the potential. And here LT, if you didn't see this part, is just the Lagrangian, okay? Lagrangian associated with the Hamiltonian flow. So this is the equation. Now I can write it into an abbreviated form like this, and here this is the symbol of this function. It's like this. And now I want to seek the WKB answer solution. Okay, suppose it's like this. Here st is a real phase function, and here phi is a sequence of amplitude function, and I substitute this into the equation, and you can just do some direct computation following Maslow computation, and you derive this equation, and here this one is just the commutation of the operator with WKB wave function, and here Rj is a sequence of a linear differential operator of order j, and in particular, if j equal to 0, R0 is just a scalar multiplication function. Okay, multiplication operator. Okay, we do the same thing. We substitute this WKB ansatz into the equation, and to the leading order. This order equation is just the Hamilton-Jacobi equation. It's like this, and here, if I write it back into the full form, it's like this. It's much more complicated, but remember that the V tilde is just the residual of a local quadratic approximation, right? So it has the value of this function at 0 is 0, and the first derivative and the second derivative are also 0. Okay, and if you evaluate this function, this equation at point x equal to 0, okay, then this term vanish, and if the phase function at the initial time satisfy this condition, you can prove it's easy to prove that at any later time t, it's still 0. Okay, it's a derivative. Because the phase function, the derivative is momentum, right? It's 0. You can prove it. And moreover, if the second derivative of this phase function is 0, you can also prove this property will be maintained for any later time t. So that means if you evaluate this equation at point x equal to 0, and if these two conditions are satisfied, then at least at point x equal to 0, you got an ODE equation. It's an ODE equation. Okay.